Hey there students, Mr. Hughes here. In our video today, we're going to take a look at a sample problem involving power. This is a problem that shows up on one of our homeworks in Quest. Quest homework 7B is what it's labeled as now, and it may change depending on the year you're watching this video. But this will deal with some concepts involving power. So the question says this. When a rattlesnake strikes, its head accelerates from rest to a speed of 30 meters per second in 0.42 seconds. Assume for... I'm not going to pick up here in 3, 2, 1, go. Hey there students, Mr. Fugit here. In our video today, we're going to be looking at a sample problem involving power. This problem is one that shows up on one of our homework assignments in Quest. Right now, that homework is labeled as homework 7B, dealing with power. That may change a little bit depending on the year you're watching this video. We're going to take a look at solving one of the problems here together. Our problem statement says this. Wayne exerts a force of 63.2 newtons to pull a 467 Newton sled along a snowy path using a rope that makes a 22-degree angle with the ground. The sled moves 48.5 meters in 4.5 seconds. Okay, what is Wayne's power? Answer in units of W, so that would be watts. Okay, so we're looking at trying to find power. Now, generally, power is defined as work done on an object over time. Now, what does the problem give us? It gives us a force on an object. It gives us the weight of a sled. It gives us an angle. It gives us a distance, and it gives us a time. Okay. Now, it does give us a time. So I'm going to make a note of that over here. The time we're pulling the sled, for me, again, your numbers are going to be a bit different. The time we're pulling the sled is 4.5 seconds. Okay? So that's how long we are pulling the sled, and we're going to use that time in our power equation. Now, to find the work being done, here's what we've got. We've got the pull force on the sled. Mine is 63.2 newtons. We've got the weight of the sled. So this is going to be Fg, or the weight on the sled. And we want to be careful that is 467 newtons. Again, because that's in newtons, that tells us it's a force, which means that's the weight. Remember, the mass is a measurement of matter. That would be in kilograms. This is a force, it's a weight, and that is how hard, Earth's gravity pulls on that object. We can use that to find the mass if we need to, but that is not the mass. I want to pay attention to that. We're given an angle, 22 degrees with the ground. We're going to draw a picture here. And then the sled moves 48.5 meters. So we got a delta x of 48.5. Okay, now we want to find the work done. And if you'll remember, there are two ways we can find work. One is our work equation. Work done on an object is equal to the force applied on the object, the displacement of the object, cosine of the angle between the force and displacement. That appears like it's going to be the best approach here because we know something about the force on the object, how far it goes, we're given an angle. So that's probably going to be the best approach. Remember, we can also use work, what we call the work energy theorem, where we can look at the change in energy of the object. Here, again, we're given more information that seems to align with the work equation, so that's probably where we'll go. Now, to visualize what's going on here, here's our sled, we've got a pull force, and we're told, again, my number is 63.2 newtons, and we're told it makes a 22-degree angle with the ground. So I'm going to assume the ground is right here, and that would be 22 degrees. Now, we were also told that there is the weight of the sled, 467 newtons. That would be the sled's weight, or the force of gravity on the sled, that's 467. Again, just because we're given that force doesn't necessarily mean we're going to use that value. We want to pay attention to what it represents. Because the question wants, what is Wayne's power, right? Meaning kind of what is Wayne doing, right? What's the work he's doing on the sled? Now, snowy path. Okay, it does say the sled travels 48.5 meters. It's not explicitly clear which direction the sled is traveling, but we can assume that the way that, Wayne is pulling, the way it's being pulled, our sled's probably going to move that direction as well. And this is technically a free body diagram, so I'll draw this to the side. We can assume our delta x is, for example, like to the right. Right? So that angle there, remember, the angle in our work equation is the angle between the force and displacement. If my displacement is to the right, and the pull force is up at 22 degrees, the angle between those two, so from our delta x to our force, would be 22 degrees. So that is the value we'll use in our work equation. Remember, sometimes we're given an angle, and just because we're given some random angle doesn't necessarily mean it's the angle we'll use. We need to make sure we have the angle between our force and our displacement, which we do in fact have to. Okay, so let's find the work here, and then we should be able to take work over time to find the power that we're looking for. So work done is equal to our force applied on the object, which we're looking at the pull force here. So absolute value of 623.2 will just be 623.2. And then absolute value of 48.5 is just 48.5 meters. And then cosine of our angle here is 22 degrees. So cosine 22 degrees. Do make sure when you plug this in, your calculator is in degree mode. Right? So we've got 63.2 multiplied by 48.5, cosine of 22. I'm getting 2,842 joules. That should be positive because we are adding energy into our system. Right? Okay. So again, you don't have to put a plus sign there. I like to just to remind myself it's a positive value for work. We're adding energy into the system. Okay, now it doesn't necessarily say, we're speeding up, slowing down. Okay, so we don't really need to worry about, we're just looking for the work done by the pulling force. We're not looking for the total work done. Again, it doesn't tell us, as we pull, are we speeding up, that sort of thing. So we can't really look at a change in energy here. We're just looking at the work done by Wayne, the puller, right? Okay, so we've got our work done. We know the time that we're doing this work in, 4.5 seconds. And he went pretty fast, 48 meters in 4 seconds. That guy's pretty quick. Okay, excuse me. So our power is going to be our work done as a function of time. Our work done we just found, 2842 joules, divided by our time, 4.5 seconds. So 2842 over 4.5. Wayne's power is 631. And I'm getting 0.5. So if I'm going to 3 sig figs, I call this 632 watts. And that's how we can find Wayne's power, given how much work Wayne is doing as a function of time. I'm going to check that here. Yep, 632. So hopefully this gets us set up on this problem on the homework. Kind of a good example of using what we know about work and connecting that to what we're doing here with power. As always, if you have any questions, feel free to let me know. Other than that, good luck.